All right, guys, let's go ahead and get started for today. So what I want to talk about today, folks, is going to be enthalpy. So enthalpy was the topic of the video that you folks watched for last night. And what you'll remember, this goes kind of back to the first quiz question, or one of the quiz questions, and that is, what is enthalpy really? Well, when you get right down to it, enthalpy and heat are essentially interchangeable for us. So what we actually said is that enthalpy is heat measured at constant external pressure. Okay, so we said, for example, if we have a coffee cup or simple calorimeter, normally if we're monitoring some process in there, that's open, right? So the idea is that that's going to be exposed to constant atmospheric pressure. So as a result of that, what we're really measuring is going to be enthalpy. But for us, heat and enthalpy are essentially one and the same. So the other thing to remember about enthalpy is that it's a state function, which heat is not, by the way. And that's one of the things that makes enthalpy very nice to work with if we can do so. So unlike heat, if enthalpy is a state function, what that means is that to calculate a change in enthalpy, all I need to know is an initial enthalpy and a final enthalpy for my process. I don't need to know what pathway was taken to get from point A to point B, or from my initial set of conditions to my final set of conditions. So that's a big advantage of working with enthalpy over heat. I don't need to worry about a pathway there. Okay, so we talked about state functions in the video. And we'll keep coming back to that again and again. That's such an important concept. All right, so just a few different types of enthalpy that you might encounter in problems. One might be a delta H. Remember, delta H is my sign or symbol for a change in enthalpy. Might be a delta H of combustion. Okay, so this is an enthalpy associated with a combustion of, say, a hydrocarbon. Now, we can kind of categorize these as we wish, as either being endothermic or exothermic. So I think we said last time, if we study a combustion reaction, for example, in a calorimeter, we know that heat is given off by the system. So we would expect this type of enthalpy to be exothermic. Okay, remember, heat's being given off by the system and absorbed by the surroundings. Another really important one that we're going to run into is a delta H of formation, which I think we also mentioned in the video. And this is one that's going to tie into the next topic that we'll deal with in much more detail on Friday, which I think is going to be Hess's law of heat summations. Delta H of formation is essentially going to be an enthalpy associated with the formation of 1 mole of a compound from its individual elements as we find them under thermodynamic standard state conditions. So we're forming a compound from its elements. Now, this can either be an endothermic or an exothermic process, depending upon what compound we're forming. In many cases, it's going to be exothermic because it makes sense that the compound, if it's stable, should be actually lower energy relative to its elements. But it can go either way. Another kind that we might run into is a delta H of vaporization, which we see as a delta H of VAP. So that's the enthalpy associated with converting 1 mole of a liquid to its gaseous state. Okay. Now, obviously, to get a liquid to go to a gas, we got to put energy into it, right? So we'd expect that one to be endothermic. And then one other one we could talk about might be a delta H of fusion. Okay, I'll put fusion here. Fusion means generating a solid from a liquid. Okay, so in other words, if we're freezing water to form ice, that's fusion. Okay, so as a result, that has an entropy associated with the process. Now, think about it. Do you have to take energy out of the system or put energy into the system to convert a liquid to a solid? What do you guys think? Think about the process you got to go through to make that happen. Are you cooling something off or are you heating something up?
Put energy into the system.
So if I'm putting energy in, I'm heating something up, right? So that would be an endothermic process like the delta H of vaporization we just talked about. So think about it. Yeah, from the point of vaporization, if I want to get a liquid to go to the vapor phase, in other words, I want to boil water, I'm putting energy into the water, right? To make it boil, to convert it to a gas. Is that right? So that's endothermic. Well, what if I'm kind of going the other way? What if I'm talking about, say, trying to condense a vapor into its liquid form? Would I have to cool it off or heat it up? What do you guys think?
You want to cool it off?
You got to cool it off. So fusion's the same way. So think about if I want to make ice from water, right? So I got water at room temperature and I want to convert it to ice. What do I have to do? I put it in the freezer, don't I? So is that taking energy out of the water or putting energy into it?
Taking energy out of the water.
Yeah, exactly. So what that means is that from the perspective of the water, that has to be an exothermic process, right? Exothermic means heat is leaving the system. Okay. So think about it from those perspectives. It's always good to do that because now you can kind of keep an eye on what the sign ought to be on each particular type of enthalpy you're dealing with. Okay, so those are just certain types. Now, the other thing I could do with any of these is I could put that little not sign up there. And remember, when I do that, what does that mean? That little not sign. We talked about it in the video. But what it means is that we're making the enthalpy measurement under standard conditions. So in other words, I'm tying down a particular pressure, and that pressure is 1 atmosphere. So I'm measuring at 1 atmosphere of pressure external. Temperature is also held constant. That's at 298 Kelvin. So that's about room temperature. That's 25 degrees Celsius. And if I'm talking about something that's in a solution phase, then I can also define a concentration. And that concentration is going to be 1 molar. Okay, so if I'm under standard conditions, I'm nailing down a pressure, temperature, and concentration. So if you see that little 0 or not sign above the delta H like that, is telling us that we're making that observation or measurement under very, very specific conditions of pressure, temperature, and concentration. Okay. And in many cases, when we have tabulated delta H's, that's what they are. They're standard state delta H's. So let's just take a look at some typical examples of the kinds of calculations you could run into when we're talking about enthalpies. So a lot of these just really kind of go back to reaction stoichiometry or mole ratios, okay? So example number 1 is pretty simple. So the question is, how much heat in kilojoules is associated with production of 283 kilograms of slaked lime, which is a fancy name for calcium hydroxide solid? Okay, so the equation is down here below. So what we can do is we can take calcium oxide, can let it react with liquid water, and you end up making calcium hydroxide or slaked lime. Okay, so I think the equation is balanced there. So everything's 1 to 1 to 1, which makes things easy. Now, the delta H associated with that reaction as measured under standard state conditions, that's a delta H of reaction, right? So it's the enthalpy associated with that reaction, is minus 65.2 kilojoules per mole. So that tells me this is going to be an exothermic process, right? Because the enthalpy of the reaction is negative. So I want to know how much heat is going to be liberated when I make 283 kilograms of slaked lime. So that's kind of where we have to start. And I'll just call it CaOH taken twice. So ultimately, I need moles, don't I? Because take a look at my delta H. It's in terms of kilojoules per mole. Okay, so ultimately, I got to get to moles here. And when they talk about the mole here, it can either be in terms of mole of reaction or the mole of formation of the slaked lime. So really, that's the thing I'm focusing on there. Okay, so let's go ahead and get from kilograms to grams. That kind of makes sense to do because if I got grams, I can get moles. So if I have 1 kilogram of the stuff, that's 1,000 grams of it. Okay, so kilograms cancel with kilograms. I got 1,000 grams of slaked lime. Now I want to get to moles of slaked lime. So let's see, 1 mole of it. I can go to the periodic table and calculate. is 74.093 grams of it. All right. And now, as I said, normally what we do is we think about this in terms of kilojoules per mole of reaction. Okay. But notice everything's 1 to 1 to 1. Okay. So a lot of times I'll reference this to per mole of reaction if they don't tell me anything else. So I know that for every 1 mole of reaction, I've got 1 mole of slaked lime. So what if I called that calcium OH taken twice? Okay, and you could have just left it in terms of 1 moles of the calcium hydroxide as well. That's fine. But moles of those cancel with moles of those. So that tells me how much heat I'm going to generate per mole of reaction. So when we work that out, that turns out to be carrying my negative through here because, well, actually, let me leave it positive because I want the end result to be negative because it's going to be exothermic. So let's see, 3819.52 moles of reaction. Now notice that once I have this, what I'm going to do with it. Now I'm going to use the kilojoules per mole to get back to heat. Okay, because that's what I'm told there. I'm minus 65.2. And that's kilojoules per mole of reaction. Okay, so notice what happens. Moles of reaction cancel with moles of reaction. Now, really the sign is kind of up for grabs here. I'm going to leave it negative because I want to show this as heat actually being given off. I'm not sure how Chem 101 deals with this. You'll have to kind of work some problems and see, because sometimes they say how much heat is evolved or emanated or whatever. You can either think about it in terms of heat given off and leave it negative, but sometimes people will just say, okay, I'm going to leave that as a positive heat because it's just a quantity or amount of heat. So it really kind of depends on what Chem 101 wants. So you have to just try it and see what you get. So I end up getting minus 2.49 times 10 to the 5th. And that's going to be kilojoules of heat emanated. And like I said, in the other parlance, if I wanted to use that, because sometimes we think about it just in terms of just an absolute value of heat, we could report it as 2.49 times 10 to the 5th kilojoules. Okay, so again, you kind of have to put an answer into Chem 101 and see what it tells you to do with the sign. All right, questions about that, guys? So you can see how it kind of comes down to knowing about your mole ratios here. It's coming down to stoichiometry. So that's something you kind of have to watch in these kinds of problems. This one was easy because everything was 1 to 1. All right. So let's look at another example here. So in this example, we want to look at the combustion of methane gas, CH4. And that's given by a combustion reaction equation, which I give you there. It's already balanced for you. And the delta H standard state of reaction here is minus 890.3 kilojoules. And they report it here as per mole of CH4 burned. Okay, so now we're referencing back to the CH4 here. That's our reference point. Okay. So the question now becomes, what mass of methane in kilograms has to be burned to liberate 2.80 times 10 to the 7th kilojoules of heat? Okay. Now, notice in this situation, they left the heat as a positive value. You know, in fact, it's going to be negative because this is going to be an exothermic reaction. Okay, so that's what I'm talking about, sort of depending on how the problem is couched and how they give this to you. You know it's exothermic, but they give it to you in terms of a positive heat. All right, so let's go ahead and start with the given here, which is going to be 2.80 times 10 to the 7th kilojoules. So now we're starting from the perspective of the heat. It needs to be at 2.80 times 10 to the 7th. Okay, and that's terms of kilojoules. All right, so now what I can do is I can go right to my kilojoules per mole, my delta H of reaction. Okay, because I want to ultimately get back to methane here. So I can use that as a conversion factor to get me there, right? So I know that for every 890.3 kilojoules of heat, okay, I'm using up 1 mole of CH4. Okay, so now I'm back to an amount of CH4 here. But what did it ask me for? It asked for a mass of it, doesn't it? Okay, so now let's see, kilojoules cancel with kilojoules. So what have we got? I need moles of CH4 on the bottom because I'm trying to get to mass. I could look up the molar mass of that, and it turns out to be 16.042 grams of CH4 per 1 mole of it. Again, that's from the periodic table. And I wanted kilograms, right? So now we can just convert grams to kilograms. So for every 1 kilogram of methane, I got 1,000 grams of it. Okay, let's make sure everything cancels as it should. Moles of CH4, moles of CH4, grams with grams. We're left with kilograms. Looks like we need, what, 3 sig figs out of this. So it turns out when I work this out, the calculator tells me 504.52 kilograms of CH4 has to be burned to generate that amount of heat. To 3 sig figs would be 504. Okay, now again, kind of got to watch your signs here, because ultimately what we would have here is a situation where we can't have a negative mass of CH4. Okay, so we could either think about this in terms of just absolute amounts of heat, or another way you could think about it if you really wanted to get picky with the signs is, okay, you're liberating this amount, make it negative. You also know that you've got a minus 890.3 kilojoules per mole, and the negatives cancel out. So either way, you're going to get a positive value of CH4, which is what you have to get. Okay. Questions? All right. So let's move on to part B here. So these are just different ways you can see the problem presented here. So the next part is what quantity of heat in kilojoules is liberated in the combustion of 1.65 times 10 to the 4th liters of CH4, because it's a gas, right? Measured at 18.6 degrees Celsius and 768 millimeters of mercury. Okay, so I could still use my same delta H of reaction, can't I? But now I got to get things in terms of moles. I've got a value of liters or volume of the CH4 at a certain temperature and pressure, right? But I need to get back to moles, don't I? Because to get back to a heat, I need to get things in terms of moles so I can use the kilojoules per mole to get back to the kilojoules. All right, so how do I get from a volume, temperature, and pressure back to moles? What should I do, guys? Remember what we're dealing with here. It's gas, right? How do I get from temperature and pressure and volume back to moles? Do we have an equation for that?
Ideal gas equation.
Yeah, sure thing. That's exactly what we do. Remember, PV equals nRT. Very good. Okay, so I can solve that for N, can't I? So once I have that solved for N, all right, we're good to go. So that's going to be PV over RT. Now, remember, the units all have to match the units of the gas constant. So I got a few conversions I've got to do. So I got to get temperature in terms of Kelvin, right? So I have what, 18.6 degrees Celsius, and I got to add to get to Kelvin 273, right? And that turns out to be 291.6. All right, what else do I have? I got to also get my millimeters of mercury over to atmospheres, don't I? Okay, so we got conversion for that, right? 1 atmosphere is what, 760 millimeters of mercury. Okay, so millimeters of mercury cancel out. And that should get me to about 1.0105 atmospheres. That should be good to what, 3 sig figs tracking along here. Technically, your temperature really is, unless I do the 273.15, your temperature is really only good to 2 there, or sorry, to 3. And I think we got everything we need. Now we can go ahead and plug into the gas equation. So let's do that. 1.0105 ATMs times the volume. That was in liters already, so we're good. 1.65 times 10 to the fourth. Okay, and then I need the R. That's the 0.08608,206 liter atmospheres per mole Kelvin, right? And temperature we said was, we'll leave 291.6 in there. Kelvins. Okay, so what ends up happening? Kelvins cancel with kelvins, liters cancel with liters, atmospheres should cancel with atmospheres. I should be left with moles, and I am. Moles are in the bottom of the bottom. Okay, so when I work this out, my N ought to be 696.807 moles of CH4. And that should be good to 3 sig figs. So we'll just underline that to keep track. All right, now we're not done yet, because what's the question really asking us for? It's asking for the kilojoules of heat. But now I've got the moles of CH4 that I burned. Okay, so now I can use my delta H to get back to that. All right, so remember from part A, we had a delta H from way up in the beginning of the problem. So what I'm going to do now is go ahead and take my N, okay, and then I'm going to multiply it by my delta H of reaction. Okay, so that's going to be what? Minus 890.3 kilojoules per 1 mole of CH4. Because remember, the problem gave this to us in kilojoules per mole of the CH4 that we were burning. Moles cancel with moles. If I keep track of my signs, obviously this will be negative because I'm emanating heat. This is an exothermic process. So minus 6.20 times 10 to the 5th kilojoules of heat were given off in this case. Okay. And again, my negative here expresses the fact that this is an exothermic process. All right. Everybody see what we did there? Any questions? Okay, so it's a good illustration of how we have to use some stuff we learned in the last chapter to come back and work these kinds of problems. So we've seen how we bring stoichiometry into it from a couple chapters ago. Gas law stuff can come in from last chapter. So you can really see how the stuff builds on itself. All right, one more before we practice a little bit. Part C says if the amount of heat that we used in part B or got from part B could be transferred with 100% efficiency to water, liquid water, what volume of water could be heated from 8.8 degrees Celsius to 60 degrees Celsius? Okay, so what are we really talking about here? Well, this is kind of like a calorimetry problem, isn't it? Where we're basically heating up water and the water is absorbing that heat, and that's going to cause a certain amount of the water to increase its temperature by a certain amount. So we got an equation for that, don't we? Okay, go back and remember, since we're talking about water, I can use Q H2O is equal to C, that's the specific heat of water, times the mass of the water, times the delta T, or difference in temperature that the water experienced. Okay, so what am I after? I want the amount of heat. All right, so what we're going to do here is we're going to calculate grams. Now, why do I need to get grams out of this? Because I want to get back to heat. And how do I have to get back to heat? Well, I get back to it through the mole, don't I? So if I have the grams of water, okay, that underwent this amount of heat change or temperature change, then I have a means of getting back to moles. And then from there, I can get to the water. All right, so let's do that. So the mass is equal to the heat divided by C times delta T. Okay, I'm going to express the heat as a positive quantity here. So we'll say 6.20 times 10 to the 5th joules or kilojoules. And remember, that was the answer from last time, right? From part B. So I want 1,000 joules per kilojoule. Okay. All of that divided by the specific heat of water, which was what, 4.184 joules per gram degree C, times the difference in temperature. So the difference between 60.0 and 8.8 is 51.2. Okay, so let's see, kilojoules cancel with kilojoules. All right, joules will cancel with joules. C with C, grams is in the bottom of the bottom, so that gives us a mass. So it turns out we're heating up 2.8942 times 10 to the 6 grams of water. Okay, and we'll watch our sig figs here. It looks like we're good to 3. So now we can go ahead and convert that back to liters. All right, because I think that's what it asked for the amount of heat, blah, 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 what volume of water. So we really want to take this back to a volume. Okay, so now what am I going to do? I'm going to take my 2.8942 times 10 to the 6 grams of H2O. Oh, and I need a density now because I need to get between mass and volume. And generally speaking, the density of water will take as 1 gram per milliliter. Okay, so grams will cancel with grams. And what I'll have here now is 1 liter corresponding to 1,000 milliliters. Okay, so that should give us liters of water, which is what we're after in the problem. We said we were good to what, 3 sig figs here. So what I'll end up with is just 2.89 times 10 to the 3rd liters of water that I have to heat up. Okay, so this is an interesting part of the problem because now we can kind of take it back to a specific heat or thermal transfer into a substance kind of situation, which is what we were studying back in the calorimetry part of all of this. Okay, so I like this problem because it ties a bunch of stuff that we've studied so far in this chapter together, which is always a good thing. All right, guys, any questions about what we did here in any of this?
I have a question.
Okay, please go.
So for part B, our answer was negative, but in part
Yeah.
C, we used that same number, but positive. So
Yeah. And
if
why
it-
did I do it positively? That's a good thing. And the reason I know that is because what's absorbing that heat? It's the water, right?
yeah,
So the water now becomes my point of focus or my system. Okay, so if the heat is going into the water, then that means I'm increasing the internal energy of the water. So that means the heat now becomes positive. So it all has to do with what my point of reference is. Does that make sense?
yeah. So what if our number in part B was positive? Would it stay positive in part C?
Well, what would happen in that case is if I had a positive kilojoules in part B, that would suggest an endothermic process, wouldn't it?
Yeah.
So that would suggest now that the heat would actually have to leave the water, wouldn't it?
Mm-hmm.
Okay, so that would change the sign. Okay, but you can't have another way to think about part C is you can't have a negative mass of water. You just can't, right? So masses of things have to be positive. So basically what we're doing is kind of just justifying that the sign is what it's supposed to be in order to get a positive value of grams of water.
Okay, thank you.
You're very welcome. Any others? Okay, let's do a little practice, guys. Hop back over to Chem 101 here. And we want to go to thermochemistry, and it looks like we got a few enthalpy problems here. So you got about, well, it says I got about 15 minutes here, so that's going to work out just about right, guys. Here it goes. All right, so it looks like we got 4 problems there to play with. Again, very similar to the kind of stuff we were just doing here. Number 2, by the way, is a good example of looking at what sort of sign conventions Chem 101 wants there. So play with that and see which sign they like to see, positive or negative, when they talk about heat being released. So you'll note in number 2 that even though the reaction is exothermic, and they say that heat's being released, which of course is what happens when you have an exothermic reaction, they like to see a positive value. So again, that's just their convention. So that's why we do these practice problems. They want to see that as sort of just an absolute value quantity of heat. Number 3 is a good problem too. Pay attention to your stoichiometry of your reaction there. Any questions so far, guys? Looks like you're doing fine on these. All right, guys, you got a few more minutes to work on this if you like, but just to reiterate, we're on Wednesday, so keep in mind you have a Friday quiz coming up on Friday. Make sure you watch the new video, which is Hess's Law of Heat Summation. Okay, anything else before we head out? All right, guys, enjoy the rest of your day, and I will see you on Friday.